listening to international investment advisor Doug Goldstein on the Goldstein on Gelt show, the financial show where we'll talk about how you can make the most of your money. With all the confusing financial chatter bombarding you each and every day, Goldstein on Gelt will give you the practical information you want and need about living a financially stable life. Here's your host, money maven Doug Goldstein.
Okay, we are back. We are talking with Professor Dan Shechtman, who is a professor of materials science at the Technion. He's also an associate of the U.S. Department of Energy's Ames laboratory and a professor of materials science at Iowa State University, and he was awarded the 2011 Nobel Prize in Chemistry for the discovery of quasicrystals. Professor Shechtman, it's a pleasure to have you.
Good morning.
I think I'm going to have to start with the very simplistic question. If you could just give us a brief understanding of what quasicrystals are, I'd appreciate that.
Okay. Well, usual crystals, which are the ordinary crystals that were discovered between 1912 and 1982 for the 70 years, have something in common. First of all, they are ordered, which means that the atoms in them are ordered, and they're also periodic. That means that the atoms are arranged in a periodic order. The quasi-periodic materials are also ordered, but the order is quasi-periodic, and that means that there is no periodicity there. Periodicity, for example, is if you look at the tiles, if you have square tiles on the floor, obviously your office has a rug, but if you have tiles on the floor like mine, then like so, okay, then obviously there is order there, and there is also periodicity. So if I stop the line and ask you to continue that, you would know how to do it, because there is order and periodicity. Now, the quasi-periodic materials are ordered, but there is no periodicity. If I ask you to continue to build it, you will not know how to do it unless you obey certain matching rules, and then there will be no repeating motif there. Mm-hmm. But there is order. And some materials, as it turned out, and not just a few, but hundreds of materials, are ordered and quasi-periodically in a quasi-periodic system. And so these are new crystals, and the discovery created a paradigm shift in the science of crystallography. Real revolution in the science of crystallography.
It seems that, as with many revolutions, there was a quite a lot of dissent amongst the ranks, and that you had to deal with a lot of people who really thought that you were not quite on the same plane as they were. Yes.
Well, in the beginning, when I was alone, there was objection among the close scientists with whom I collaborated. But then, when I published the first couple papers with colleagues, immediately there was a positive reaction from the scientific community. They joined force, and from there on, we still had to fight for the truth, but I was not alone anymore. Mm-hmm. And the other thing is that I was very certain that I'm correct from day one. and the only objection was irrelevant as far as I was concerned. But the objection continued for quite a few years. First, among the International Union of Crystallography, which was the body that governs the science of crystallography. But also later on, when they accepted it in 1987, publication was 1984. Discovery in 1982, publication in 1984, and the acceptance by the International Union of Crystallography was in 1987. Still, there was some opposition that was led by Professor Linus Pauling, an eminent scientist, probably the most important chemist in the 20th century. And he continued to object, and he never agreed.
Did he eventually retract his objection, or
no? He eventually died.
And it's a form of retraction, I guess.
Well, it's a brutal form of rejection. Yes.
All right. So you were very brave, really, to continue to go against the powers that be. That's certainly in an academic position. if you are really the person saying that what everyone believes is not true and no one agrees with you, that could threaten your job as well. How did you feel? How did you gather the strength to continue fighting for what you knew was right?
Well, it was not too difficult. It depends on character. In the beginning, when I was really alone, okay, so they, nobody came with experimental proofs that I was wrong. They just said, this animal cannot exist, okay? And they showed me a book to read, and I said, my crystals are not in the book, okay? It's something else. But then it became easier and easier, and we were a group of young but eminent scientists from around the world, and we were the avant-garde. First, I was the avant-garde alone, but then we were a growing group of scientists from around the world, including people from the United States, obviously, not many in fact, but also from France, many from France, Germany, China, Japan, and many other countries. And our ranks grew continuously because there were, at first there were a few scientists, then tens of scientists and hundreds of scientists and thousands of scientists, and the opposition just was shrinking and shrinking and shrinking and shrinking until they were gone.
We are talking to Dan Shechtman, who is a professor of materials science at Technion. He also won the 2011 Nobel Prize in Chemistry for quasicrystals. He's described a little bit from a chemical standpoint what they are. As this is a financial show, my day is that I'm a financial advisor, so I'm always looking for the angle. What is it about this quasicrystal that might eventually find its way into our day-to-day lives?
Well, if you want to introduce new materials into products, that means finding applications for a new material, you have to find a special property which is unique to that material, in which that material is very good. And usually it's a combination of properties. So there may be chemical properties and physical properties, and price and appearance, and it's a combination. If you have a winning combination, then you can introduce this material and start using it for making a certain product or making a certain part in a product. Quasi-periodic materials have certain properties which are interesting, and they have already found their way into industry. For instance, there is a steel, a very strong stainless precipitation hardening steel made by a Swedish company named Sandvik, and that steel, the designation is 1RK 1RK91, and that steel is extremely strong. It is ductile. It is stainless. It is precipitation hardened. It's a wonderful steel, a very, very strong steel, and it's being used in electric shavers. All the parts that are moving there and the parts that touch your skin made of this steel, and they use this steel for many other purposes. They use it in operation rooms, in surgeries, and so on. Any part, if you need a steel to touch the body, outside or inside, this is a very good steel to use. And then there are many other applications. So what's special about this steel? What is special is that this steel is strengthened by tiny little particles which are quasicrystalline, which are embedded in the steel, and this makes the steel very interesting and very it's very useful for many applications. Other uses use, for instance, the fact that these quasi-periodic materials, some of them are non-stick material. You can use them instead of Teflon. Other properties are, for instance, the heat conductivity is very low. They're insulators, good insulators. If you need to insulate from high temperature, then you can use these materials as coatings, and then it serves as an insulator. So there are properties like this, and some have found their way to the industry. I wouldn't get a Nobel for the application. The Nobel is for the paradigm change in the science of crystallography.
I see. So are there any particular companies that you think are capitalizing on this concept in a big way that investors should be looking at?
Sandvik is one. I don't know. It's not. Sandvik is a huge company. This is just one product. So I don't think it affects their income very much. But but it just shows you that they know how to make business. Other companies, Saint-Gobain in France owns now some of the patents on quasi-periodic materials, which I know were at least tried to be used in car engines and so on. Then there are many other uses, but not something like which is extremely powerful. I think that the most profitable product now is the Sun-16.
Mm-hmm. Okay, so let's talk a little bit about your background and also about Israel in general. You certainly are a pride of Israel and all Israelis because of the Nobel Prize that you have won, but also because there have been many Israeli Nobel Prize winners. You grew up in Israel, you were educated here, your whole science background was really developed here. Do you think there's something, A, special in what you got, and B, does Israel continue to give that to its students today?
Well, let's talk. Are you asking me if there will be more Nobel laureates eventually? I mean,
no. My question really is: are my children going to be Nobel laureates because they're going through the Israeli school system? Are they learning science as well as you did?
Depends on the school. If some schools teach excellent science, other schools do not. So it depends. And the problem is that the science is not equally taught well in each and every school in Israel. And this is something that I try to change. I think that science should be taught from a very early age, from the kindergarten age, preschool, through elementary school, through secondary school, so that when they reach the academia, when they reach universities, they have a feel for science and they like it. And this is a transformation that we have to undergo. As I said, some schools teach excellent physics, chemistry, mathematics. Other schools, definitely not.
Yeah, I'm a little worried. I think that when we see that Israel is not as successful as it used to be in terms of, America isn't either, in fact, but in terms of the level of science that comes out of it, that's what concerns me.
Yeah, you're right to be concerned about it, and so am I. We'll have to work and change it. Now that I have more access to decision makers, maybe I can make a difference.
Okay, I hope so. As we are nearing the end of our time, just tell me, what's your next project that we should be looking for?
Scientific science project, you mean?
Yeah,
or anything, something for the benefit of mankind?
I'll take either one.
Okay, well, let's talk about benefit of mankind. I'm trying to push one or two agendas, not only in Israel, but also in the world. And one important one is technological entrepreneurship. I believe that technological entrepreneurship is the key to a success of a country. Israel is a good example. We have good entrepreneurs. We have a very high percentage, a very high ratio of engineers per capita. And now Israel economy depends on the startups that young engineers, usually young engineers, start and make. So how am I involved in that? Several ways. Number one, for the last 25 years, I have been teaching a class here at the Technion named Technological Entrepreneurship. And by now I have about 10,000 graduates who took that class, and all of them are engineers. So that's quite a number of people who were infected with the bug of entrepreneurship and are walking free in our streets, and I hope that they will infect other people with the same bug. Israel has become a startup nation. Do I have a major part in it? I don't know. I want to hope that I do, but I cannot measure that. But I know that many of my graduates opened startups. So that's one thing locally. Internationally, come November, I will organize at the Israel Academy of Sciences an international meeting for Asian countries on a technological entrepreneurship. We want to bring them here and hear about their experience and tell them about our experience in Israel about opening startups, but also about teaching entrepreneurship. And entrepreneurship is taught in several places in Israel. I may be the first to do it properly, but now there are other places in which they teach entrepreneurship, and we want to teach it to the world. If we have something to teach the world, it's probably this thing here. Everything else you can learn from the world.
All right. Well, we look forward to learning that. We have been talking to Dan Shechtman. In the last few seconds, can you just tell us how can people continue to follow your work?
The scientific work, you mean?
The scientific work.
All over the world. There is work on quasi-periodic materials, and there are almost annual international conferences on quasi-periodic materials, and then there are binational conferences and national conferences. There's a lot of activity in this field, and because there are so many quasi-periodic materials, different quasi-periodic materials, there's a lot to be studied, and hopefully some of them will prove interesting also from the application point of view.
Okay, that sounds fabulous. Once again, Dan Shechtman, Professor of Material Science at the Technion and 2011 Nobel Prize winner in chemistry. Thanks so much for your time.
Thank you.
You've been listening to the Goldstein on Gelt show with money maven Doug Goldstein. Doug's weekly radio show is heard around the world, but if you miss it, you can download the podcast at www.goldsteinongelt.com. The Goldstein on Gelt show gives you up-to-date financial ideas so you can get on the path to financial freedom. If you'd like your questions answered on the air or off, send Doug an email to doug@profile-financial.com. It's your money for your future, so join Doug every week to build your wealth on the Goldstein on Gelt show.